tradition with this sort of slot is we sort of bring an expert from the field to talk about some of their research, often sort of state of the art. And we're very pleased to have Marc Deisenroth here today. So Marc has been doing GPs ever since, when did you start your PhD?
2006 or something.
2006. He did his PhD with Carl Rasmussen, and starting, I guess, in Tübingen and then moving to Cambridge. And his thesis is about a really interesting area of reinforcement learning with Gaussian processes, trying to sort of do control, that sort of domain. And he still does a lot of work with robotics and GPs. But today he's going to tell us about some work he's doing in scaling up Gaussian processes, something we're all very interested in. And this is an approach Marc has for getting Gaussian processes distributed across many processors and working with millions of data. So over to Marc.
Thank you, Neil. Also, first I want to thank Neil and the entire group here in Sheffield for organizing this. You should do this every year, twice maybe. So that's a really good idea. So given that Neil already explained what I'm going to talk about and pretty much summarized the entire talk, we can straight go to the pub. And the reinforcement learning stuff I'm going to talk about tomorrow, in 2 days in the Bayesian optimization workshop, which has nothing to do with Bayesian optimization. Okay, so as Neil said, I'm going to talk a bit about distributed Gaussian processes. How can we scale up Gaussian processes if we deal with slightly more interesting data set sizes than 100 data points? So this is pretty much my outline, and I'm going to keep the Gaussian process section. It doesn't work?
No, we're
okay.
about this screen here.
Okay.
Don't like looking at you.
Oh, okay. Yeah. So I'm going to keep the Gaussian process section reasonably short, and I'm going to cut a lot from the sparse Gaussian process section because James pretty much talked about this already. And then I'm going to explain what we mean by a distributed Gaussian process and what kind of properties these things have. A disclaimer just at the beginning, this is reasonably new, so there's a lot of things that I actually don't know, we haven't explored yet, but that's probably lining up. Okay, so in a Gaussian process setting, we are interested normally in a regression problem, solving a regression problem. So we assume we have n observations yi, which are f of xi plus epsilon, and epsilon we assume is ID Gaussian noise. So just the most easy thing you can assume is pretty much going to be throughout the talk. And the idea is to find a distribution over functions, so p of f given some training data x and inputs x and observations y. So in this particular plot, the observations would be these crosses here, and the corresponding inputs would be their the projections onto the horizontal axis. And a Gaussian process is a good solution for this particular probabilistic regression problem. So I think after 2 days of GP workshop, I believe we can assume that at least parts of the audience agree with this. So I'm going to step immediately into the Gaussian process training here. So when we train the Gaussian process, we already came across the marginal likelihood. So it's the probability of y given x, and the hyperparameters where we integrate out the latent function. And if you write down the marginal likelihood and you want to find hyperparameters that maximize the marginal likelihood, so we usually maximize the log marginal likelihood because it's much easier numerically and in general. So if we write down the log marginal likelihood, it consists of like 2 terms. So this is the this green term and the orange term. Who is colorblind again? Can you distinguish? More or less? Oh, he says yes. Okay, I discard everything on that. Okay. So the nice thing, the marginal likelihood is a nice thing for an automatic trade-off between a data fit term, which is this y transpose k inverse y, and the model complexity. So Neil was also talking about this a bit earlier. So the nice thing also is that if you want to optimize the marginal likelihood with respect to these hyperparameters, you can compute the gradients with respect to the hyperparameters analytically. So the hyperparameters are kind of hidden like in this K matrix. And then the gradient of the log marginal likelihood with respect to the hyperparameters is given by this particular expression. And depending on what kind of kernel function you choose, this term changes, but that's all that changes. The computational complexity for computing the marginal likelihood is n cube for computing the determinant of the kernel matrix and for inverting the kernel matrix itself. So that's where the computational complexity comes from. And when you optimize the hyperparameters, you can't cache these because these matrices change. Every time you tweak one of these parameters, you compute a new kernel matrix and you have to do the inverse again. Okay, when you do predictions at a particular test point, then this predictive posterior distribution is Gaussian, and the equation for the mean and the variance are given here. And here the computational complexity is a bit smaller, because now you can cache K inverse and K inverse times Y because they never change for as long as you don't add more training points. And then the mean prediction can be computed in O of n, so it's a linear in the number of data points, because this is just sorry, this should be Y. This is a typo. Let me just quickly fix this. I'm wondering where this is. Ah, there we go. Just do a quick compile and then we should be back on track. Yep. Right, so now we cache this guy. And we have a scalar product here. So this is just linear in the number of data points. And then this can be computed in quadratic time. So this is nice. But so linear and quadratic if you want to compute the mean and variance. So Gaussian process have tons of applications. So Bayesian optimization pretty much is what is, I think an entire day is about Bayesian optimization on Thursday. So, or you can say also experimental design. I mean, it's pretty much, I think it's more or less the same. The idea is you model an unknown utility function with a GP and try to maximize this performance function in as few experiments as possible. There's also something in robotics and reinforcement learning where you can either model value functions or predictive dynamic models with Gaussian processes. I'm going to talk about this on Thursday as well. Or data visualization. I'm not sure whether Neil would coin it as data visualization, but if you look at the GPLVM, it's an extremely useful tool for data visualization if you have a latent space that is two-dimensional, which can be nice, which can be used for plotting, for example, these like poses of motion capture poses in a two-dimensional space. So very useful applications. There are more applications. There's just like 3 of them. The problem with Gaussian processes is computation and also memory complexity. So we mentioned already earlier, training scales scales cubically and prediction scales quadratically, and the memory requirement is n squared for storing the kernel matrix, or half of the kernel matrix if you store Cholesky factors, and n times d for storing the data set itself. So the practical limit for running full Gaussian processes is about 10,000. It can be a few thousand more or less, but that's the ballpark number when I stop working with Gaussian processes, because not even mainly for computational reasons. I mean, it takes a few hours to train a Gaussian process with that many points, but my RAM just doesn't do it anymore. So that's the end. So there are 2 approaches, I think actually orthogonal approaches. I'm going to discuss a bit how to scale this, or how to push this limit of 10,000 data points a bit further. So in sparse Gaussian processes, okay, let's maybe use the whiteboard a little bit. So a Gaussian process definition says if we have a bunch of bunch of function values, all of these function values are jointly Gaussian distributed. Yeah, So we have many function values. And so it's like 2, 4, so about 10 data points. And in the 10-dimensional space, all of these guys are Gaussian distributed. So this should be represented by this kind of factor graph. So these are all function values, so training function values and test function values. And this black box kind of like connects them and makes them jointly distributed. That's how I read this thing. And then the GP prior is we're looking at the joint distribution between the training function values and the test function values. So the nice thing with the GPs is if we always have finite number of training data points, and we also always have a finite number of test data points. You can choose an arbitrary number of test data points, but it's always finite. And if you write this joint distribution of training and test data points down, it's always a finite distribution. That thing is Gaussian. So the prior, I assume, is mean 0, and then this is this big covariance matrix, where this is the training covariance matrix. This is the test covariance matrix, and these are the cross covariances between training and test set. So, and this is a potentially extremely nasty to compute. That's the reason why there's a red box. So this is a thing that scales n cubic. So what James mentioned earlier, these sparse methods that use inducing inputs, they pretty much say, oh, I'm going to take my original function values and I'm just going to throw in a couple of more. And I call these things inducing function values, so called FU. So there's also still connected to this black dot. So everything is still Gaussian distributed. Just come up with some other function values that fall into that Gaussian distribution. And then the idea, I would say, roughly speaking, is to compress the real function values into these inducing function values, and ideally in some way that is a lossless compression. So that means if I only saw these red dots over here, I could theoretically recover all the training function values and the other function values that I pretty much threw away. So that's more or less the idea of all kind of like sparse Gaussian process methods that use these inducing inputs. And I'm going to completely scratch this stuff. It's just a different way of doing the sparse or a different sparse approximation. So James mentioned the variational sparse approximation. This one is the FITC sparse approximation. It's more or less the same thing. They use these inducing inputs as a different way of like learning these inputs, but more or less the same thing. So summarizing the inducing input methods, and so this particular one, they use these inducing inputs and they optimize these the corresponding input variables such that the approximation gets better and better. And you can do this by maximizing the corresponding marginal likelihood. So this inducing input approximation gives you an approximate marginal likelihood which you can optimize with respect to these inducing inputs. And then so instead of maximizing this marginal likelihood with respect to the hyperparameters only, you also optimize this with respect to the U values. You then end up with a relatively high-dimensional non-convex optimization problem, because instead of optimizing d hyperparameters for d dimensions, you optimize an additional m times d parameters to optimize the locations of these inducing variables. So that can be quite complicated. And there's an example from a paper that I just copied from Ed Snelson's paper, and the approximation works really nice. It's good. So the sparse approximation typically approximates a Gaussian process with n data points using a model that uses only m much smaller than n hypothetical data points. And the selection of these m data points can be very tricky and can require a solving a rather complicated optimization problem. You can also just choose a random subset selection from your data and just say, okay, I choose 500 data points from my 10 million data point data set randomly. That's actually not the worst thing you can do. And it's quite simple. So computational complexity for these kind of methods is nm squared. So James mentioned that one earlier. If you choose just m data points at random, you get away with m cubed. So that's even better. Practical limit. So if we say the practical limit for a normal Gaussian process is n equals 10,000, so the number of data points is 10,000, I would say the practical limit for the number of inducing inputs is also 10,000, roughly. In practice, we choose m actually much smaller than 10,000, more like in the hundreds, maybe around 1,000. And if we set m, so I spoke a bit about compression. So if we can compress 100 original data points into one of these inducing variables, then this pushes the number of the data set size of the original data set to about 1 million. And I think this is also the maximum I've seen, order 1 million, few million data points. But that is pushing the limits quite far. At least for the time being, I think that is, as a ballpark number, is about right. So now I'm going to go into this, into the idea of distributed Gaussian processes. As I mentioned earlier, this is a bit, it's not super robust or super stable at the moment, but I think it's worthwhile discussing as an alternative approach or orthogonal approach to the sparse Gaussian processes. And this is pretty much work by Junwei Ng. Unfortunately, he graduated and left to finance. So that work is based on his master's thesis last year. Anyway, so one of the things I mentioned earlier was like the thing that is really complicated, or one of the things that is really complicated to compute is the inverse of this kernel matrix. So assuming we have a data set here, we need to compute the inverse of the kernel matrix. But the idea of these distributed approaches is pretty much to chop this data set up into bits and pieces, and then you compute the corresponding kernel matrix, which would be an approximation if you make sure that these pieces are independent. So then this kernel matrix would end up as a block diagonal covariance matrix. Inverting this just requires inverting these individual blocks, which is cheap, depending on the size of the block, but it's cheaper than this. And let's assume we just split the data set completely randomly into m of these chunks. If we then place m independent Gaussian process models, and I'm going to call these ones experts probably more often in this talk, and then we can distribute the corresponding computations across different nodes, different computers, different, almost said planets, but continents in that case. So you can have a really large distributed system if you make this independence assumption. Yeah, so then this Gaussian process expert could compute a couple of predictions here in Sheffield, and this one down in London, and this one in New York, for example. And all of these predictions are independent, and afterwards you need to combine them somehow, and I'm going to talk about this a bit later. So the nice thing again is the block diagonal approximation of the kernel matrix. Inverses are easy. The log determinant is easy. So that makes things much nicer. And then once we've done all of this, we need to combine these independent predictions to an overall result. So that's the high-level idea of this distributed Gaussian process stuff, and Neil summarized that earlier pretty much. So now let me talk about how we train these things and how we do predictions with these kind of models. So if we have our original data set of size n, if we split this into chunks m chunks, each of size p, and we make the assumption that all of these Gaussian process experts that operate on these chunks are independent, then the marginal likelihood factorizes, and the log marginal likelihood is is approximated by the sum of the marginal likelihoods, which can be computed at each expert or by each expert, independent of the other experts. So that means distributed optimization in training is really straightforward. So if we assume that we share these hyperparameters, the Gaussian process hyperparameters across experts, so every expert has the same hyperparameters, then every expert computes a gradient of this log marginal likelihood, so and sends it to a central node, and the central node just sums up all of these gradients and then propagates the gradient update back to the individual nodes. So it's really, really straightforward to do the optimization. And the computational complexity is now m times p cubed. So p is the size of the data set at each expert. So it still scales cubically, but p is now much smaller. And we have m of these experts. So this is m times p cubed. That's where that's come from. But this is distributed over many machines, and many, to be more precise, is m machines. And the memory footprint is mp squared plus nd. So I still need to store the entire data set somewhere, and I can theoretically store this in chunks. That's fine. But I only need to store the kernel matrix, the small kernel matrices, or the Cholesky factors of these kernel matrices. And that is where this p squared comes from. And compared to n squared down to m times p squared, I think it's actually quite a big advantage. So if you assume that, just an example, n is 1,000,000 and p is 100, that means we have 10,000 experts, each of which has 100 data points. That's fine. So just empirical training time to see how far we can get with this. So to compute this, we computed how much time it takes to compute the marginal likelihood and the gradient of the marginal likelihood with respect to the hyperparameters. Because this is kind of proportional to the overall training time if you do some sort of gradient descent. So the training data set size is on the horizontal axis here, and the computation time of the marginal likelihood and its gradient is shown on the vertical axis on the left-hand side. So the full Gaussian process is in red, and so this is about, I think, 16,000 data points. It takes about 100 seconds to compute the marginal likelihood once and take the gradient. Here, this one is the sparse Gaussian processes with the number of inducing inputs set to 10% of the size of the data set. So there we get to about, I think, 30,000, 60,000 data points if we take these 100 seconds as a ballpark number for computing a gradient. And if we then, the distributed methods scale a little bit more favorably here, and we get to about 16 million data points if we keep increasing the number of experts. And that number of experts is, in this graph, is shown in this black line here, so we end up with about 1 million experts in this example. So the full Gaussian process with 16,000 training data points scales approximately as the sparse Gaussian process with 50,000 data points, and approximately as the distributed Gaussian process with 16 million data points. So this is just to say that this method is actually practical for training on really large scale or large data sets. That means we can actually push the practical limit by some bit. Yes, please.
How many experts are running in parallel?
So that depends. So this one was run on our computing cluster at at Imperial. Having said that, that definitely downplays that statement. I can give you other numbers later. So that was, I think, 64 computers with 4 cores each, something like this. But I can run experts, I don't know how many, like a few thousand easily on this laptop. So that is not too bad. Okay, so right, so practical, yes.
Yeah, on the previous slide.
This
Distribution.
this one?
Yes, here this formula. So, well, there is this summation, but where the approximation?
Ah, okay, right. So so we started with P of y given x and theta, and the approximation is to write this down as a product of pk of yk given xk and theta. And so equals 1 to the number of experts. That's the approximation.
But isn't it so that it is like strict equality because the
No.
data points are independent?
No. No. So if that was the case, then of course, it's the first slide I'm showing, right? Here. Then all of this would factorize immediately. So you would ignore all the cross covariances that you have in your kernel matrix, if it would factorize that way. Okay. Yes.
I'm trying to get a bit of an intuitive grasp what it really means to throw away all that covariance information, really, because you throw away at least half of it, right? If you have 2 blocks, and then you can have more blocks and just throw away even more. And so, I mean, that sounds amazing, to be honest. So, what's the impact of this? And
I mean, it's a rough approximation.
so, because especially at the points where in the matrix, where the kind of the corners of the block
Yeah.
matrices are, you lose every.
Yeah.
I mean, deliberately you use every dependency.
Yes. So there are some cases when this approximation is not the worst thing you can do. So one thing is when your data naturally clusters in input space and you have a stationary covariance function. And then you run some clustering first, and then you make independence assumption between these clusters. Then this works reasonably well. Or you have super redundant data. Then it doesn't really matter.
But then you could also just subsample.
You could also subsample.
Okay.
But I think this one is a bit more expressive than just subsampling.
But actually, I was wondering about this because if you subsample, you kind of. No, actually, I don't know if it makes a difference because the kind of dependencies that you throw away if you do a subsampling is different from the kind of dependencies you throw away when you do this kind of.
Well,
stuff, right?
in the subsampling case,
Using a kind of a regularity of what you throw away, right?
So is that a...
No.
Okay.
Well, I was going to comment on that, but
Oh, yeah, sure. I mean, go ahead. I don't have to answer all
No,
these
okay,
questions.
no, I was just gonna say, you can also see it sometimes as a benefit, right? Because the types of covariance function, especially when you're using RDFs and stuff, actually those really, really long distance interactions, which is just basically a, how do I say? Well, it's actually not a positive thing that you're actually getting them there. So if you're picking these, like often we see these clustered behaviors, right? And now you're naturally getting like a truncated Gaussian, right? That's basically one way of seeing that you're getting it. But doing that in itself is quite hard to put that covariance function in. So
Yeah, so
it
there's...
might not be a bad thing to remove those if you can sort them correctly, right?
Yeah. Yeah. Having said that,
Yeah.
we usually use random subsampling, random distribution that completely destroys all spatial relationship that you may have. If you use spatial properties, the approximation is much better. Yeah. Okay. So in practice, training with a data set size of about 1 million in one dimension requires about 10 to 30 minutes on a laptop. So I tried that out yesterday on this laptop here. Training with about 5 million data points in 8 dimensions on a workstation with 12 cores takes about 4 hours, where the star means training means maximizing the marginal likelihood and stop when converged. And converged means after usually about 30 to 80 line searches, and each line search takes about 2 to 3 evaluations of the marginal likelihood and the gradient. And that usually computes in, well, n cube. I should call this p cube in this case. So I'm not going to change that right now. But, oh, sorry. No, this is correct. Usually n cube. If you train a full Gaussian process, that would scale n cube. So that's not too bad. And the nice thing here is we only optimize one set of hyperparameters, meaning the optimization is relatively easy. Okay, so now that we know how to train this model, the prediction case is a bit more complicated. Because now imagine that every single expert now produces a prediction with some mean and some variance. But they're not identical, unfortunately. So there's a question of like how we combine these, for example, these 3 means and variances to an overall result of this of the full model. So I'm going to look now or discuss 4 models for doing these kind of like combinations of individual predictions. There's a thing called product of experts models, a generalized product of expert model, the Bayesian committee machine, and the robust Bayesian committee machine. I'm going to go through all of these models in more or less details. So the objectives, or the things that we want from this model are, in the first place, all of these models for predictions should be able to scale to large data sets. But that is already covered by the training procedure. So I'm just going to tick that box here. Ideally, we also have a good approximation of the full Gaussian process, which I'm not going to, now I'm going to use as the ground truth model because I want to approximate the full GP as closely as possible. The predictions should be independent of the computational graph. So computational graph, I have 2 of them over here. So each of these computational graphs has 27 nodes or leaves. And ideally, independent of how I chain these computations together, the result here and here should be the same. So this is potentially interesting for people or companies with really large-scale infrastructure. So it's not what I have available, but potentially, you can come up with some companies who have large-scale infrastructure who can run computations on in different continents, where you would like to you would like to say, for example, compute this stuff in Europe, this one in Asia, and this one in North America, and then push together somewhere centrally. You don't want to do all. You don't want to do the. You would like to have relatively short communication distances here. So if network traffic is a problem for you, then this property of being independent of the computational graph is quite appealing. Okay, and that also means you can run the same kind of model on different computing infrastructures. So for my laptop, I would probably choose a model like this, but if you have a really large-scale infrastructure, you might be choosing this kind of model. But it gives the same answer, ideally. And also we are interested in reasonable predictive variances. So that's one of the nice properties of the GPs, are the variances. If we screw up the variances, then we can also use an SVM. So the variances are interesting. And all the applications I mentioned earlier, data visualization, the robotics part, and the Bayesian optimization part, they all live from these predictive variances. So that is really, it's a really interesting and important property. Okay, I'm going to use this kind of model or this kind of example as a running example where I have a bunch of data points here. So these observations are these circles, and I can fit a full Gaussian process to it, so which is 95% confidence bound is given by this shaded area, and the posterior mean is this black line. And now I'm going to look at all of these 4 models that I mentioned earlier and see how well they approximate this particular Gaussian process. So the other models are trained in the same way. It's just the difference is only in the prediction. And for all of these models, I'm going to go to a really extreme case with each expert having only 2 data points assigned. So every single expert only knows about 2 data points, but I have a lot of these experts. So I think I have 128 data points here, so I have 64 experts with 2 data points each. Yeah. Okay, so the product of experts model is relatively simple. It just says my predictive distribution is just the product of the individual predictions. So each of these predictions is Gaussian because it comes from the Gaussian process from each expert, which is written in this way. And the nice thing is, again, you can write down the overall precision and the overall mean of this particular or of this product here. And the precision is just the sum of the individual precisions. So remember, the precision is the inverse variance. Yeah? So we just sum up the inverse variances from each expert, and we get the inverse variance of the overall model. That's easy. You just need to sum these things up as linear in the number of experts. And for computing the mean, we take the mean of each individual expert, divide by the variance, and we sum these things up, and afterwards we pre-multiply by the variance of that we already computed before. So this is also relatively cheap. So the computational graph, I thought it might be easier to do this on the whiteboard. I think there will be enough equations coming up before the pub night starts. So let's just give a relatively simple example. So we have one central node and 4 experts. Okay, let's make this a block. So this particular model should give us the same prediction as this model. So the same number of experts, but here we first combine 2 of these predictions into this one and 2 to this one, and then we combine these 2. So we have a slightly, well, we have one more hierarchy level in the hierarchy here. But if we now take, so if this is P of F star, this is the product of I equals 1 to 4 of Pi of F star. So we can write this as, P1 times P2 times P3 times P4. And we can bracket them, push this to here, push this to here, and that product here ends up over here. That means we can do this, and this particular model is then independent of the computational graph. And These are the corresponding equations, but I think that picture is maybe a bit easier. Yes?
Can I ask, is it obvious, well it's not, I mean it's not true is it, that the thing on the left is a density?
Oh yeah, sorry, yeah, this is there's a proportional sign here, and we can compute the mean and the variance in closed form. Yeah, that's a good point. Yeah. So if you now think about stacking a lot of these models together and get like a much deeper hierarchy, you could think about it in this way, where you have the Gaussian process experts, and then you have how many product of experts models sitting on top of each other and just using the computations from the subtree that belongs to them. That is how you can do this. So we have a model now that scales. It's independent of the computational graph and doesn't perform very well. So the problem here is, I mean, the data fit looks actually quite nice, but the variances don't make any sense. And the reason for this is exactly that point. So the overall precision is the sum of the precisions. And if you have 1 million experts saying, oh, mean 0, variance 1, then you just sum up all of these precisions, and the precision will be 1 million. So the variance is going to be 1 over 1 million. So every time somebody says, I don't know what's going on, I don't know what's going on, I don't know what's going on, you get more and more confident. That is what this model does. So yeah, so the more experts, the more certain the prediction, even if every expert itself is very uncertain. And that means this model cannot fall back to the prior if you use more than one expert. If you use only one expert, this model is identical to the full GP. So that's unfortunate. Okay, so here's a potential fix. Question? Okay, here's a potential fix. This is called Generalized Product of Experts. So here we take the product of experts model and just put a weighting factor in here. We call it beta k. And the beta k weights the confidence of each expert. And the equations for the precision change a little bit by scaling each individual precision with this beta k factor. And the same term appears also here when we scale scale each mean. So it's a similar updates to the product of experts model.
Does the beta depend on the input location?
Yes, sorry, yeah, that is slightly sloppy notation. So the beta k depends on x star. So the beta k is actually a beta k of x star. And if we set the sum of the beta k to be 1, then the model can fall back to the prior. And then this model is also called a log opinion pool model. So they have been around for 20 years or longer, at least 20 years. So computational graph, I'm going to be a little bit short about this. It's also independent of the computational graph. It's a bit more nasty now with like these beta k vectors, beta k values, but it is possible as long as you make sure that you normalize the sum of or set the beta k's to 1, or the sum of them to 1. Then otherwise you would lose the property that you fall back to the prior. So there's an issue with this, because ideally we need an a priori setting of the beta k values. Otherwise you would need to send messages around where beta 1 tells beta 2 what its current value is, and beta 2 adapts to this. So you have a lot of traffic there. So you need an a priori setting to avoid this, and one of them would be just to set it to 1 over m, where m is the number of experts. Okay, so now let's do this. And that is the corresponding prediction with this model. So it does fall back to the prior, and the mean is identical to the one of the product of experts model, but the variances are a little bit too, let's say, conservative. So even in the area where we have a lot of data, the model is really uncertain. So it's better than the other model because it's not overconfident, but this one is underconfident. So then there's a model called the Bayesian committee machine, which has also been around for 15 years. Here we make an additional, let's say, at a high level, we use Bayes' theorem when we combine predictions. So currently we only use Bayes' theorem when we compute the marginal likelihood and we do some sort of like training procedure there. But when we combine these predictions, we don't really use Bayes' theorem. So the Bayesian committee machine looks a little bit at this, and it makes an independence assumption that turns out to be useful. They say the data set of expert J is independent of the data set of expert K given the corresponding function value. And if you do this, it turns out that your predictive distribution looks like this. So it just multiplies all of these predictions together again, and then it divides m-1 by the m-1 times by the GP prior. So this one is the GP prior, and these ones are the posterior predictive distributions of all these experts. So it's the product of expert model divided m-1 times the prior. That's the BCM. And if you look at the precision, it's exactly the same as the product of experts model. You just subtract m-1 times the precision of the prior. That's all. And the same, more or less the same update equation for the mean once you computed this one. That's all. Yeah, that's the point. So this one is also guaranteed to fall back to the prior. So intuitively, really only intuitively, you have m models in the numerator, and you divide out m-1, leaves one model. So it's a kind of like normalized model that is left over. That is just an intuitive statement that might motivate why it falls back to the prior. I'm going to skip this again. It is also independent of the computational graph for the following reason. We already showed that the product of experts model is independent of the computational graph. So if you just propagate everything through to the root and do the normalization just at the root node, fine. Then, so this one would be the stacked model for the BCM, and this happens only at the root node, the normalization. And it looks actually quite reasonable. The variances look amazing. So they grow when you leave the data. They are really small when you're in the data. And then the mean has some funny properties that are unfortunate. And so usually, I don't know, my limited experience with this model is that it works reasonably well when you have a lot of data points. But when you have, like in this case, only 2 data points, and these experts are relatively weak, then they contradict, and then the mean can have funny properties. I can illustrate that a bit more, but offline, because I don't have too much time left in this talk. But generally we think this model is quite promising, and so our idea was to robustify this in some way. And what we thought was we kind of like merged the idea of the generalized product of experts, where we weight each prediction with the confidence of each expert, and the Bayesian committee machine.
Just a question on the previous image. So here you also did randomly split this data.
So in this particular example, I did not randomly separate the data. I just took a class, say linear. So the first 2 data points on the left-hand side go to the first one. So it's not. So this one is spatially structured. It's not random. Yeah. If you did it randomly, you would get similar behavior.
Okay. Right. Even the overshoot of the mean there in the middle.
Yeah, this one is the really odd one.
Yeah.
Yes, that one is not atypical. It happens in many cases, even if you do a random assignment of the data points.
If we're randomly selecting them, each of our individual GPs is going to have a much longer length scale, but we're then aggregating these GPs with longer length scales. Is there any sort of intuition as to how that comes back to the original one?
Yeah, so I haven't actually done too much analysis of this and compared the length scales of this model with the length scales of the original model. So ideally they are the same, but I would say they're only similar. I don't think you can actually recover them. And it depends on the split. So usually I would think that these length scales might be a bit longer, tend to be a bit longer if you do random data set splitting than the length scales of the original model.
You mentioned robustifying the model. I was going to ask if you tried including one data point and more than one expert.
Yes, that works. So the question was, can you assign one data point to 2 experts or 3 experts? Yes, so we started actually with this, and then it was a bit unclear why we shouldn't make the data sets of each expert bigger initially. And we haven't found an answer to this question yet, but yes, so that definitely helps.
This is basically an ensemble method, and like in random forest, you don't do separate.
Yeah.
You don't have one data point in just one tree. You have it in several.
Yes, but I could also just use twice the size of the data set at each expert. And then the question is which one is better, and I don't know.
And so it's as if it's kind of like a multiplicative model combination, right? So if I take a single draw from 2 GPs, it's kind of like multiplying them together. So if I'm trying to do what some people do and put like a structure on my covariance, so I know, for example, it's a polynomial of order 3 in the first place. Now I have multiple experts. That bound on the differentiability or the order of the functions that we're trying to draw from disappears. Is that correct?
Oh, that's a good question. So if you use a Martin 3-2 or something, then you have a 1 times differentiable model. Do you lose that property? So if you I would say maybe not. So, but this is I mean so the overall precision is just the sum of the individual precisions. So that model, I believe, should be fine. But then the means are weighted by the individual precisions, and things are getting a bit tricky.
Yeah, so we're summing the means and the variances, but that's actually because we're multiplying the probability distributions, which means we're multiplying the function spaces, I think. Which means I think we do lose well, I wasn't sure.
I'm not sure either.
Okay.
Neil, do you have an idea whether we lose that property?
No.
Okay. All right, but yeah, I don't know. That okay. Okay. So yes. No, go ahead.
So one question. You mentioned that your data is clustered.
Yes.
Then what you're doing is basically to assume that if 2 points are close or in the same component, they have a covariance k.
Yes.
If they are not, they have a covariance 0.
Yes.
That defines a covariance structure over the whole space.
Yes.
Why not use the simple GP equations with this kernel?
With a compact support kernel.
Well, would be some kind of.
Yeah.
Would be a sum of the kernel times indicator functions. And then that gives you a sum of GP predictions.
Yes.
And the variance right as a sum as well.
Yes.
Did you consider that?
No, I believe these models would be equivalent. Yeah, if your covariance structure looks like the one I showed earlier with this block diagonal, and if you have some sort of a compact support, then everything in the support of would be in this block, and everything outside would be 0, wouldn't you?
It doesn't exactly need to have compact support.
I mean, that I also need to think about this. Sorry.
I think Rasmussen in their unifying view of sparse Gaussian processes say you can't do that because of the transductive nature of the Bayesian computing machine. He's not talking about or BCM, but of BCMs generally, and that if you fix if you make predictions on fixed points, then use those points to make predictions on your next points, then it relates back to FITC, but there's no direct covariance that makes the two of them.
Ah, okay. Okay. Cool. Thank you. Okay. So yeah, so what we wanted to do is like combine these ideas of like pretty much introducing this weighting factor into the Bayesian committee machine. The equations change a little bit, so we have now this generalized product of experts in the numerator, and instead of like having m minus 1, we subtract we have sum of beta k minus 1 in the denominator. Again, this is a normalized model. So it is guaranteed to fall back to the prior. The predictive precision and mean are given by these equations, which kind of like combine the generalized product of expert model, which is this red box, and this funny version of subtracting the GP prior 1 or adding 1 minus sum of beta k, the precision of the GP prior. So that comes out if you use this kind of model. It is also independent of the computational graph by seeing that the top is a generalized product of experts model, which is independent, and then you do the normalization at the root node. So if you look at this stacked model again, so you first have the GP experts, then you run one Gaussian generalized product of experts model, and then you just keep forwarding or propagating the sum of beta k's of the subtree up to the root node. And everything in between is a product of experts model. So this is how you can implement this. So it's independent of the computational graph, even for arbitrary beta k's. So they don't have to sum up to 1. We take care of this by this normalization at the end. So if they sum up to 2, then we would just subtract, well, in that case, 1. That's fine. And if we look at the predictions with this, this is an old graph. Predictions of this, then, so the variances make sense. And in the area where we don't have any data points, the mean and the variance also makes sense. So that models seem to be a bit more promising than the BCM and the GP or E and the product of experts model. So that's a good thing. Yes?
In terms of robustness, if you just increase data set size to 4 or something like that, does it make a dramatic difference?
I think not in this particular case. It wouldn't make a dramatic improve, or it would not dramatically improve the BCM. But if you scale it up to like 50 or something data points, then the BCM recovers. Okay, so now we're looking at empirical approximation errors of these methods. So we looked at a relatively small data set of 10,000 data points where we can still train a Gaussian process. So we ran this only on a single computer. Here we have the gradient time in seconds, and this is the RMSE. So if we look at the Gaussian process, which is this dashed black line, this is the baseline that we want to have. If we train a Gaussian process, we get an RMSE of about 0.1, and we train for about 1,000 seconds, so for computing the marginal likelihood once and the corresponding gradients. If we choose a subset of data points, then we get this graph here. So if we choose 2,500 data points per expert, randomly sampled 2,500 data points, you get an RMSE of about 0.3, and this one is maybe 750, and so on. So the number of data points is approximate is written on the top horizontal axis. And the other models are pretty much identical in terms of RMSE for 4 experts in 2,500 data points each. And then they slowly start diverging. So the star, so the POE and the generalized product of experts model are identical because they have the same means. So that makes sense that the RMSE values are identical. And then the BCM and the robust BCM are performing slightly better than the product of experts models. And the robust BCM performs better than the BCM for probably reasons that are due to these kind of effects. So at the end, we are looking at 39 data points per expert in a, I think, 7 or 8 dimensional space. That's not that much. And the gradient computation time is, so this is a second, and this is almost nothing. So it's really fast computing this model, but the approximation error is quite big. So if it comes to negative log predictive density, so if we look at P of y star, then we are not looking only at the mean approximation, but also at the how much sense the variance predictions makes. And in that case, we see some very different behavior, and we see that the BCM at some point takes off, and this is when the weak experts kick in. So then you have these effects here where the predictive log likelihood is horrible because you can't explain it anymore with the predictive distribution, and the robust BCM still performs reasonably well, and the generalized product of experts model initially is relatively poor because it has these unreasonably large variances. But these unreasonably large variances kind of like protected at the end when you pretty much have no data points and the model is relatively bad. But with these large variances, the mean doesn't make too much sense, but with the large variances, that's okay. And the product of experts model really suffers from this underestimation of the variances, and the BCM we already discussed. So if we look at larger data sets, so we're looking at here like 700,000 data points in 8 dimensions. So this is a data set I got from James. Then we perform also reasonably well. So this is the variational methods, variation sparse methods James was talking about earlier. And here we're looking at RMSE values again. So here we have the robust BCM, the BCM, generalized product of experts model, and the product of experts model, where we did random data assignment to each expert, and we reran the experiments, and so we get some error bars in here. So the robust BCM, the generalized product of experts model, and product of experts model, they perform very similar across the experiments, whereas the BCM has a lot of variation in here. But these models don't perform too bad, at least not compared to the sparse methods, and that, I think, is a very encouraging thing. So then you can say, well, if you don't distribute them randomly, so if you do something better and pre-cluster the data, so we did some clustering with KD trees, then the performance for the BCM and the robust PCM increases significantly, whereas for the product of experts model, it doesn't really matter so much. I don't know why exactly that didn't make much of a difference, but at least for the BCM-based models, that really helped. So I would say that's a good idea to do that if you can.
And do more data points in your experts increase the performance?
Yes.
If so, is the sparse approximations and your approximation mutually exclusive, or can you be using local experts that are in fact,
yes.
the variational?
Yeah. So this is a really interesting thing. So if you have a data set that is like a few billion, you can run sparse methods at each Gaussian process expert, and then you can combine all of these models together. So that would be quite interesting. And that's why I said initially it's not exclusive. This is an orthogonal approach. And so you can combine these models if you want. That is, it's not a bad idea if you have really large data sets.
My question is formulated in my head. Let's see if I can make sense of it.
Okay.
So now you're doing maximum likelihood estimation of the parameters.
Correct.
And it seems like, because I'm still thinking about that mean going off in on the curve, and it seems like, so it does really depend at least in that case of how you split the data, because just of how it can depend on what ends up in an expert. It will either under or overestimate the length scales. So, and clustering here is, well, it's going to be expensive to do these things. So, isn't there an idea of thinking of doing a map estimation of just having a prior on the length scales here, in order to, if you have an idea of over what spatial scale the points need to communicate?
Yeah, I mean, if you put a prior on the length scale, I mean, you can theoretically also just integrate it out.
Yeah.
I mean, that model doesn't prevent you from doing this. So you can do anything that you can do with a normal GP, you can do with this model. I hope. So,
on a related note, I was going to ask if you tried to decouple the length scales of the experts.
so you have individual length scales for each expert?
Learn them individually.
No, we haven't tried this, and my fear is if we did, you would end up with like overfitting at every single expert. So if you share these parameters, okay. So a couple of answers to this question. First, we wanted to approximate only a normal Gaussian process with a single. It's a nice stationary Gaussian process, and we don't have with individual length scales per expert, you get much more flexibility into your model, which can be really good. But the problem is, if you try to do maximum or type 2 marginal likelihood, maximum likelihood of estimation of the parameters on 2 data points or 10, then I mean you probably played around with the code and you can see what can happen if you don't have many data points in a GP. So then you have problems, or can have problems. If you share the hyperparameters, kind of like every single expert regularizes each other to some degree. And they come to some sort of like average agreement that is built in.
It wouldn't make sense if you use only a very small number of data points per expert, but in this example, with using the 4,000 experts with
Right.
700K data points,
Yeah.
might not be the case.
In 8D. But you could do this, but we would have another 4,000 times 8 parameters, so 32,000 parameters that we want to optimize if you push it to the limit. That makes it more complicated. Yeah, so in terms of computation time, computing the gradient 13 seconds on a workstation with 12 cores, so that trains really quick. I do have a very short, poor demo. After I saw that we're using IPython notebooks, I hacked something together yesterday night, and I hope it runs. It's probably not going to, but so this is okay. It's already dead. Okay. No. Oh, good Lord, if I knew where that was. Ah. I don't know where it was. Does it recover automatically? So I haven't used this before. Okay, apparently. There we go. Okay, so first I'm just going to make this a bit bigger. First I'm just going to import a couple of packages. Here we have, 100,000 data points. This is, 1D, that doesn't really matter. We generated training and test set. Here we define the architecture, so we have pretty much this kind of model with 1,000 experts, so 100 experts, 100 data points per expert. And here we say random assignment of data points to experts, and this rep1 means, who asked the question earlier, like sharing data points? So if you put it to 2, then each data point is assigned to 2 experts. So, but now this is only 1. Okay, whatever. All right, so now it's training, so we can probably come back in about an hour, but that gives. So if you see this this blue bar disappearing, just let me know, because this is the computation. But I can finish my talk in the meantime. Okay, so let me quickly summarize. So there are some very interesting ways of scaling Gaussian processes. So there's one's the idea with the inducing inputs, so most of the sparse Gaussian process is based on these inducing ideas. And here we discussed a way of distributing computations. And we can go beyond the million data points size data sets. The model is conceptually extremely straightforward and very easy to train. The key is really just distributed computation. I mean, all the math and something is relatively straightforward, but it's also relatively easy to explain. So it's, Neil can summarize this in 30 seconds. This is awesome. I really like it. So the largest data set we tested it on was about 10 million or 15, 16 million. But I think it scales to arbitrarily large data sets if you spend enough computing power. So let's quickly have a look at this other thing. So it's still running, but I can take questions in the meantime.
I was just wondering what kind of approach you use to choose beta.
Yeah, that's a good question. The beta values. So we haven't explored too much, but we set it at the moment to the, let me answer that question first. To the difference in differential entropy between the prior and the posterior, which ends up being subtracting the log standard deviation of your prediction from the log standard deviation of the prior. So the more confident you are, the bigger is this difference. It means the more weight you have in this model. Okay, so this model now trained. I still have RAM left. That is also good. So it trained in 108 seconds with these 100,000 data points. Now we do some predictions and some plotting, and this is the. Just zoom out. Okay, it's not. So the data points are plotted in this. Are these black dots? So it's like. I mean, you don't need 100,000 data points to model this function, but the posterior model would give us a mean that is this red function, and the 95% confidence bound are these two yellow lines. So in many cases it looks actually quite reasonable. There's some areas here where it's maybe not quite that as good as it could be, but it's a pretty decent fit, and it's 100,000 data points trained in less than 2 minutes. So that's not too bad. Okay, so I take more questions. There's a question over there.
I just get it confused. From the complexity, it's somehow isn't it the same as Sparse GP? Because you're saying it's the capacity is MP cube, right? P is the number of data on each machine.
Yes.
So if M times P is the number of data size, then it's still the number of data and the cubic of the data on each machine, projection of the time the projection of the
Oh, no, no. So it is. It's O of P cube times M. And N equals M times P. Yeah, okay.
If you said then, if you for smart GP, you said the number of inducing input equals to the data on your machines, then they have the same capacity.
Yes. So I can distribute this heavily. So that makes it really fast.
But for smart GP, you can distribute the data. Just like Gaussian and
So I still think this is okay, let's do this. So you have M times P cubed, which is M times P squared, which is then N times P squared. So, and if you now say, okay, the number of inducing inputs corresponds to the size of your thing, so that then the computation is right. You scale identically. It's correct.
So if this scales compared to the same level, but empirically that they scales very differently because you can have a very different constant in front of it, right?
So empirically, I said in the sparse Gaussian process, I need to compress my data somehow into these inducing inputs, whereas here I can just increase the number of experts. So I can keep the resolution. So I can keep P constant. I can just increase the number of experts as I go along. And that makes it makes the approximation a bit rougher, but it scales.
There's a way of thinking of this, like if we had like the kind of effective degrees of freedom scale, we have our GP right in the middle. But as we start going on to our sparse approximations, we move further and further down to like smoothing out data points almost. And as we use this approximation, we move the opposite way so we keep the fine detail, but we lose the kind of the global structure. And so you're making approximations that is going in opposite directions.
So with the sparse methods, you model local patterns. I would say
global patterns, but no local, or fewer local.
So I would say you model more local patterns than where you have in the places where you have these inducing inputs. Whereas this model potentially gets the, depending on the distribution of the data sets, but it might be able to model global patterns more accurately than local patterns. But if you do the clustering beforehand, then you have local patterns, of course. But who's that? Is James still floating around here? No. Okay. Oh, I think he starts first.
So maybe this just reveals that I didn't understand Gaussian processes fully yet. But what I cannot wrap my head around is, you said, I think I understood that you said that the selection of points you choose for each tiny Gaussian process here doesn't really make a big difference. So in your demo, you just use random ones, right?
I use random ones for two reasons. One, it's easy to explain, and B, I can show that it works with random as well. I'm not saying it works better.
No, not better, but I'm even surprised that it works as well, especially in the one-dimensional case, right? Because in a high dimension, all the data points are kind of neighbors of each other because of the high dimensionality.
Mm-hmm.
But in the one-dimensional case, that's not really the case. So if you have a length scale that's a lot smaller, then the range of your data, why it actually works? That you, I mean, equally well already. Because you cut out these interdependencies essentially, right?
Yeah. So if you, I mean, we agreed we agreed earlier that we have 90 minutes. So if you have very weak experts, then they are very confident at their respective data points, and then they just say, I don't have any idea what's going on if I leave these data points. So you always have an expert that is somewhat confident about what is going on in a particular area of your space. So if you have one expert that is trained on these points, so it's confident here, but it doesn't really know much in this area, assuming we have a nonlinear fit here. Whereas this other Gaussian process, which is trained on the pluses, is more confident in this area. So if you do the weighting of the predictions, you take more of the prediction from this expert that knows more about what's going on than compared to the one that doesn't really know what's going on. So this is where these beta k factors come into play, where you kind of like automatically choose to ignore some of the predictions of the experts that just predict what the prior tells us to predict. That is one explanation.
Thank you.
I just wanted to ask, what about this online safety? Can you update parameters if you receive the new batch data?
So now I can say we can do everything we can do that we can do with Gaussian processes. So that means if we have a good solution to online updating of the parameters with a normal Gaussian process, we can do that here as well. But I think we can't.
Yeah, I don't know. There's not an obvious.
I mean, the hyperparameters are a bit more tricky. If you have trained hyperparameters, you can do low rank updates of the inverse kernel matrix, but changing the hyperparameters if you have a stream of data coming in is not entirely trivial. And that model doesn't make it easier. Okay, so you need to take the questions or organize the questions because.
Well, I was just going to say, I don't know what time's the social.
Yeah, it's at 6:30, so we are all leaving from here.
So
people assigned to the group today, we are leaving together at 6 from here.
And at 6 o'clock from here, walking from here.
Yeah.
Okay, so just be aware. I'm just sort of thinking with the time, you need to be slightly aware of that. Will they struggle to get back in the building? Where are you going to leave from? Front of mapping?
Maybe that's the best.
Because they'll start closing down the building at 6.